the photoelectric effect is an effect that was known for quite some time, and basically what happens is if you send light onto a surface, okay, what will happen is electrons will be ejected from that surface. So if you were to just summarize this, light will eject electrons from, now it didn't happen with necessarily everything, but from light sensitive surfaces, it would happen. And we actually use this today. Anyone know the context that we use this? Where we shine light onto something and we get electrons out of it, moving electrons out of it. Okay, solar energy, solar like solar cells, right? You shine light onto solar cells and it turns it into electricity. So that's the same concept here that we're talking about. Alright, so anyways, a guy comes around, his name was Albert Einstein. Maybe you've heard of him. So Albert Einstein basically came around and said, we can use the photoelectric effect to prove once and for all whether light is a wave or light is a particle. We can prove once and for all using the photoelectric effect whether light is a wave or light is a particle. Okay? Now he just did this in his head. We call these thought experiments, meaning he just did the experiment in his head and came up with a conclusion. Eventually someone comes around, and actually that guy was Millikan. You guys remember Millikan? The oil drop guy. So Millikan comes around and actually did the experiment in the future. I think it was about 10 years or so later after Einstein thought it up in his head. And that happened a lot with pretty much everything Einstein did. He just did it in his head. Someone later proved that it was right. So here's what Einstein did. Let's make three little columns here. We're going to have our variable. We're going to have if light is a wave, this is what should happen. And if light is a particle, this is what should happen. And I'll explain kind of, where people are coming from for each. Alright, so let's start with the first variable, and we're going to be using the photoelectric effect. So the first variable would be intensity. So in other words, let's see what happens if we increase intensity. And by intensity, what do I mean? The brightness. So increase intensity or the brightness. Okay, so if light is a wave, a brighter light means, well, which of our characteristics of light does brightness for a wave? What characteristic of a wave touches on the concept of brightness? The amplitude, right. So if light is a wave, then as we increase the brightness, we should be increasing the amplitude. Right? So this would be a dim, this would be a bright light. Alright, so here's the idea. If we send these two forms of light towards our surface, okay, we send dim and we send bright light. These have higher amplitudes. So what should happen is, and the way wave theorists explain the photoelectric effect is they said, well, as the waves come in, they basically jostle the electrons up and down. They cause the electrons to be ejected that way. Okay? And so the greater the amplitude, the harder it's going to jostle or move the electrons, which means the speed of the ejected electrons should be much, much greater. So the higher the velocity, the higher the amplitude, or the brighter the light, the more electrons are going to get jostled about, and the faster that they would be ejected. So that was the conclusion then. If light is a wave, increase it by increasing the brightness. This means there's going to be a higher amplitude or a greater amplitude, which means electrons would be ejected faster, or we could say with more kinetic energy. So if you come in with these, these high moving waves, you can picture like at the ocean, if there's a giant 20-foot wave that comes at you, it's going to thrust you about, right? Versus little, inch waves, they're going to barely mess with you at all. So this should go with a higher frequency. Now, higher velocity. Now what about the number of electrons? Well, if you look at my wave, since the wavelengths are the same, you can picture like each crest is going to eject an electron. So if I'm sending in 3 crests and 3 crests, what should happen to the number of electrons? They should be the same. So this is going to eject 3, right? This is going to eject 3. This is going to eject 3. But these are going to be moving faster. So if light is a wave, by increasing the brightness, you should eject electrons faster, but they should be in equal numbers. Okay, equal numbers of electrons. All right, what if light is a particle? So if light is a particle, by increasing the brightness, actually let's just go back to the problem we just talked about. We used a 50-watt light bulb, right? And that gave us a certain amount of photons per second. What if I used a brighter light bulb? What if I used a 100-watt light bulb? What should happen to the number of photons per second? It should be greater, right? There should be more photons per second. In fact, how many more would it be if I went from 50 to 100? Twice as much. So for particles, by increasing the brightness, let's say these are our particles, right? A dim bulb might look like this. Maybe there's 3 photons. A bright bulb might look like this. Maybe there's 6 photons. But basically the brightness is defined by the number of photons. The brighter the bulb, the more photons are. Okay, so what's this going to do to the ejected electrons? Well, if I have 3 incoming photons, how many electrons should get ejected? If I have 6 incoming photons, how many should get ejected? 6. Okay? So that's what Einstein predicted. If light is a particle, then by increasing the brightness, this means there's going to be more photons. So we would define brighter light as more photons. In that case, there will be more electrons ejected. And then what about the speed of the electrons? Well, according to Planck, E equals hf, right? So these are all the same light. So it's all like blue, for example, meaning they each have the same amount of energy, which means what should be true about the kinetic energy of each electron? It should be the same. So they should be ejected at the same speed. Okay? So equal kinetic energies. Alright, so that's one variable. Hopefully you can see that these are very different results. In fact, they're pretty much opposite results of what we should see. But Einstein went even further. He used another variable. So the other variable was frequency. So increase frequency. And that would be like the color, for example, okay, or the type of light. Okay, so light is a particle, or light is a wave. Let's do that one first. So if light is a wave, increasing the frequency, so we send in light maybe that looks like this. Okay, this might have a high frequency, and then maybe light that looks like this, trying to make the amplitudes about the same to our surface, right? So this would be high frequency, low frequency. Alright, so what should happen? If light is a wave, what should happen? More electrons. Good. So notice there's like 1, 2, 3, 4, 5 crests. If you imagine each oscillation, each crest ejects an electron. Maybe this one's going to eject 5, and maybe this one's only going to eject 2. So if light is a wave, you should expect more electrons. So increasing frequency, right? So that would be like, I'm going to write it as more crests. Okay, because the wavelength's smaller. You should suspect more ejected electrons. Imagine each crest ejects an electron. And then since their amplitudes are the same, what should happen to the speed of each electron? It should be the same. So it's hitting them at the same, with like the same force. So even though there's more of them, they're going to be moving off at the same speed. All right? Okay, what about light as a particle? So what happens if we increase the frequency? Well, E equals HF, right? So if we increase the frequency, now I'm going to keep the brightness the same, so maybe there's 3 photons, but maybe these are 3 bigger photons you can think of. Okay, maybe this is violet, and this is red. So these have a greater energy. Because E equals HF, this has a high energy, this has a low energy. Okay? So first of all, what's going to happen to the number of ejected electrons? No change, right? We sent in the same brightness, 1, 2, 3, 1, 2, 3. There should be 3 for each. What should happen to the speed? Which one should go faster? Or will they be the same? Violet should be faster. And why should violet be faster? Yeah, conservation of energy. If this comes in with 1 joule, this comes in with 3 joules, right? This is going to be ejected with more energy than this. So this conservation of energy, if you come in with more, you need to end up with more. And so that's why these would be moving faster. Okay, so the end result, if you increase the frequency, that means higher energy photons, which means faster ejected electrons. But what would be true about the numbers? Same. Alright, so hopefully you guys can tell that these are very different conclusions. In fact, they're kind of opposite conclusions, right? So when we perform this experiment, it should be very, very clear based on the results, what to conclude from it. There's actually a third part to this. This has to do with the minimum for ejection. Minimum energy for ejection. So here's what I mean by this. If we go back to our surface, so we have all these electrons. Now why don't these electrons just fly out on their own? Because they're bonded to big positive nuclei, right? So there's big positive nuclei here, and they're attracted because we know opposites attract, right? So they don't just fly off up by themselves. So what has to happen is when you're sending in either photons or waves, they have to overcome this attraction. So there's a certain attraction between them. If you can overcome this attraction, you can get them ejected. And so this is what we refer to as the work function. Basically, this is the amount of energy needed to eject. So they don't just eject on their own. You need to send in a minimum amount of energy needed to eject them. Donovan or Simon? No, he's taking a test. He said he didn't need to leave till lunch. Okay. Your mom's here. So just hurry up. Okay, this is the minimum amount of energy needed to eject electrons. And once you overcome that, then they can be ejected. So anyways, going back to this, if light is a wave, what's going to provide the minimum amount of energy? Is it the brightness of the bulb or the frequency of the bulb? The brightness. Okay, in other words, if you shine a real dim, let's say you shine a 10-watt light bulb on the surface, maybe there's no electrons ejected. And you increase the brightness till you reach 50 watts, and then all of a sudden there's going to be an ejection. So as you increase it, and think of it conceptually, if you just have little waves jostling about, right, maybe this isn't enough to get the electrons to leave. But if you send in a giant wave, okay, think of waves at the beach, right? Maybe little waves are not going to knock you over, but a 20-foot wave is going to knock you over. So the larger the wave, it's going to be enough to knock you over. All right, anyways, so a minimum brightness, and then what about light as a particle? There would be what? What provides the energy here? Frequency, right? E equals HF, so there's going to be some minimum frequency. In other words, maybe I shine red light onto the surface and nothing happens. And then I shine green and nothing happens. And then I shine blue and all of a sudden electrons get ejected. And they're ejected whether it's a 1-watt bulb or a 50-watt bulb. Okay? However, if I shine red light on it, maybe if they're not ejected. Even if I send a 1,000,000,000-watt light bulb of red light, there's still no ejection. Okay, so hopefully at this point you guys should know the result. So when this experiment was done by Millikan, which one happened? Was it this or was it this? Light is a particle. Okay, light is a particle. So when this experiment was done, basically this is exactly what happened. So in terms of the conclusions, in terms of what you need to memorize, what happened with the particle side, because the wave side didn't happen. Okay, light is a particle. So that brings us back to the question, okay, is light a wave or is light a particle? Okay, and the answer is light is both. Okay, light is both a wave and a particle. We sometimes refer to this as wave-particle duality. So in other words, sometimes it acts like a wave, sometimes it acts like a particle. And so we like to put things in like a nice little box or categories. It's this or it's that. But sometimes things are just both. Okay, it's both of these things at once. Okay? Well, it just does occur at the same time. It just sometimes it acts like a wave and sometimes it acts like a particle. And just to give you a preview, we're going to learn later on that maybe particles are also waves. Things that we think that are particles, maybe those are also waves as well. All right, let's go back to let's derive the equation for this, for the photoelectric effect. And actually, you could probably do this conceptually. For example, let's say I sent in some light, and I like to draw my photons as sperm-looking things, okay? This is the particle part, this is the wave part, right? So it's a dual nature of light here. Anyways, here comes our light. Let's say it comes in with a certain energy of 5 electron volts. Okay? Here's my little surface of electrons. Let's say this has a work function of 2. So we could just derive the equation using conservation of energy. If I want to know what is the kinetic energy of the ejected electron, well, how would I do it? Comes in with 5, right? It takes 2 electron volts just to get it to eject, which means how much is left over? Conservation of energy, 3. Look at that high level math. So we come in at 5, it takes 2 just to eject, which means 3 electron volts is what's going to be ejected. So that would be the kinetic energy of this ejected electron. So if you kind of just get that concept, even though I'll give you the equation, it's really a simple basic thing, right? Now what if I sent in 1 electron volt? What would happen? Nothing would happen. Yeah, it needs to have at least 2 in order to eject it. So if you just set in 1, it wouldn't happen. Like red light or something, not enough energy, it wouldn't eject it at all. Okay, all right, let's derive the equation then. So you guys do it for me. Kinetic energy, let's just do it conceptually. Kinetic energy of electron should equal what? Energy of the photon. How did we come up with that number 3? What do we do? Okay, we subtract the energy of the photon minus the work function. So we'll just put this in formula form. Ke of the electron equals the energy of the photon minus the symbol we use for work function is called phi. It looks like that. And that would be our equation. Okay?